Okay, everyone. Well, here's our lecture for today. I decided to do a voiceover PowerPoint because I stopped recording for part of the lecture today. So this is going to have all the information from our lecture today. It would just be a little bit abbreviated, but have all the main information again. So last time we talked about evolution, the source of Earth's biodiversity, and I mentioned that evolution is something easily understood, but it's quite easily defined actually. And we can identify it simply as genetic change in populations of organisms across generations. And that the way that we're most interested in this happening is when it happens via natural selection, where the traits that enhance survival and reproduction are passed on more frequently than those that are not. And we have many, many examples of this that we've seen in real time now. And the idea is that this has led to the biodiversity that we see across the planet. So I think it's interesting when an idea comes along and is independently put forth by two different folks. That really tells you that its time has sort of come. And so with the idea of evolution by natural selection, the intellectual framework was there before this idea emerged. And so I want to talk about one of those backgrounds, and it had to do with the work of Thomas Malthus. So Malthus was an English clergyman, and he looked at what he saw in Victorian England, and this was a time when life was tough. There was a lot of people and not as much food to go around. Starvation was rampant. And he realized that resources can increase, but not very fast. On the other hand, the reproductive potential of any species is exponential. That just means the rate of increase gets faster and faster. And we can understand this when we think of, for instance, two people that have two children makes 4. All right, again, we multiply that by 2. Each pair has 2 children. That's 8. And 16, 32. And so we see that this rate of increase gets faster and faster. So because the population grows faster than resources, the idea is that not all will survive. Only a fraction will survive to reproduce. So, as Malthus said, this system equilibrates via starvation and misery. And if we were to look at it graphically, it looks something like this. So we've got time on our x-axis and just number on the y-axis. And the idea is that, again, population increases exponentially, resources linearly. And so early on, everything's fine because there's plenty of resources to go around, population is low. But when the population goes beyond a certain point, what Malthus calls this point of crisis, then there's no longer enough resources to go around for everyone. And at that point, who gets to survive? And so Darwin took this idea and applied it to nature and said, well, the individuals that are able to survive and reproduce are those that have the best fit to the environment, those that can acquire the resources best and are able to survive to reproduce. So we'll look at an example of beak length in soapberry bugs. So soapberry bugs are true bugs, hemipterans, which means they have mouth parts that are modified to puncture and feed. And so these soapberry bugs feed on the inside of fruits. So their natural food resource had always been the fruit of this flat-podded golden rain tree fruit. Well, the balloon vine fruit was introduced to Key Largo in Florida. And when researchers looked at beak length of the population of soapberry bugs where these balloon vine fruit had become established, they found that it was significantly longer than that of the population feeding on the flat-podded golden rain tree fruit. So this was different. This originated from the population above to below. And so the researchers asked, what was it that caused this pattern? So for this to be evolution, 3 things would have to be true. The first is that variation in a given trait would have to exist in the population. So in the example of the soapberry bugs, there's variation in beak length. If we look at the length of the beak, the population on top and on the bottom, we see a little bit of overlap. So you can imagine if individuals in the population above find their way out to Key Largo, not all of them are going to be able to feed on this balloon vine fruit. Only the ones with the longer beaks are going to be able to. And so if only those individuals survive to reproduce, then over time, if there is a genetic link, then we would expect the offspring to have longer and longer beaks. So the second condition for evolution to occur is that the variation has to have a genetic basis. If it isn't, if it's something environmentally related, say it's based on the nutrition of the food that they're eating, then those traits won't persist in the population. It'll be all environmentally dependent rather than genetic. And then the final thing that has to be true for evolution to occur is that the variation in the trait must affect reproductive success. And so before you can reproduce, of course, you have to survive. So often survival is how that's affected. And so, of course, the soapberry bugs with the longer beaks and the balloon vine fruit were able to feed, and so then they were able to survive and reproduce, whereas those with the shorter beaks were not. So in this case, a given trait, which is beak length, has evolved over time. All right, so that's how evolution works. But how does it give rise to new species? So that happens through the process of speciation. And there's really two different ways that this can happen. The first is what's called allopatric speciation. This is when species form due to a physical separation of populations. So for example, we have squirrels in the cartoon on the right. Imagine on the top that initially we have one population of squirrels that's distributed across these two mountains and also on the plains below. Then some event comes along that raises the water level. Right? This happened, for instance, when the glaciers started to melt after the glacial maximum 15,000 years ago. So as sea levels begin to rise, it floods the area between those mountains, and the squirrel populations are cut off. Well, over time, when they're cut off, evolution happens. Genetic change in those two populations over time. Now, it might be random. It might just be that certain individuals reproduce more than others on one mountain than the other. Or it could be driven by natural selection. Let's say there's a predatory species that's on one of these mountains and not the other. That might cause the squirrel to evolve, say, a different color to hide from the predator, or something else. But however it happens, it leads to genetic change over time. Okay, well then how do we know that speciation has occurred? Well, when the barrier is removed and the two populations can mix, if they're separate species, then they're not able to produce viable offspring. So we know that it's been speciation when mixing happens of the individuals, but they're not able to interbreed. So allopatric speciation is the case where species form due to a physical separation of populations. There's a physical barrier that separates those from interacting one with the other. I'll just add, this is by far the most common type of speciation. The other type of speciation we can see is what's called sympatric speciation. Sympatric speciation occurs when species form from populations that are reproductively isolated, that is, they don't interbreed, but they're not physically separated. There's not a barrier that separates them. This is quite uncommon, and some folks even argue that it doesn't happen. But one of the examples that we have where it likely happened is in the East African rift lakes with the cichlids that we talked about. So cichlids, for instance, have evolved to feed on different things in different parts of the lake. And so because they're feeding in different parts of the lake, they don't come into contact. Now there's no physical barrier separating them, but just because of the way they live ecologically, they become reproductively isolated, and over time genetic change can happen separately in each of those populations, and given enough genetic change, when they come back together they won't be able to reproduce. So sympatric speciation, much more common, but it can also occur. So we can look at patterns of species diversity around the globe, and these are a number of species of amphibians. And we might notice, as was mentioned in class, that we have higher species diversity around the equator, around the Amazon. With these amphibians, we've got decent high species diversity in the southern Appalachians. You can see the warm colors there. Similarly, we could look at patterns of vascular plant species diversity. So plants that transport chemicals and food throughout their bodies. Similarly, we might say, most of the areas of high species diversity occur along the equator. So we have these patterns of the number of species around the globe. And so we might ask, what has led to this, right? How has evolution led to different numbers of species in different areas? So there's a few different hypotheses that can clue us in as to a region's species diversity. The first is what's called the time hypothesis. This is just the idea that communities that have been undisturbed for longer periods of time tend to have more species. So for instance, in northern latitudes, again, 15,000 years ago, the last glacial maximum, there were these giant ice sheets that covered the ground. And so as those glaciers receded, as they melted, as the climate warmed, species had to disperse into the open habitats left behind by these glaciers. In the tropics, that wasn't the case. There weren't any glaciers down there. It was too warm. Then there's the area hypothesis. It says that larger areas have more species. And why is that? Well, as we discussed in class, one of the reasons is that there are more different kinds of habitats available, and also simply that larger populations can be supported in larger areas, which makes extinction less likely. Now, the clearest example of this is on islands, where we can ask, how does the number of species on an island vary with island area? And so these are examples with a couple different groups of animals that show that, we generally find a positive relationship between area and species number. Then there's the productivity hypothesis. We talked about NPP and how it varies around the planet. And so you might predict that greater production in plants would lead to greater species diversity, because we have more energy at the bottom of the food web, so that allows us to add more trophic levels, even though we're losing energy at each trophic level, right? And when there's more productivity, we might just expect there to be more plant species as well. So here's a case study looking at algal species on boulders in the intertidal zone near Santa Barbara, California. And so as I mentioned in class, often biologists have to study questions on smaller scales so that they can extrapolate that to larger scales. So this author might really have been interested in how species differs among islands or among continents, but you can't conduct experiments at that scale, and so they decided to ask this question looking at boulders in the intertidal, a much smaller area, more manageable experimentally. So the first thing he noticed was that these boulders are moving around in the surf. And so the smallest boulders move around a lot, the largest boulders hardly at all. So that was a dynamic that he thought might be important. So then I asked y'all which boulders you would expect to have the most species of algae and why. And there were some folks that voted for each one. But certainly the area hypothesis would predict that medium or large boulders might have more species. Whereas the time hypothesis might predict that medium or large boulders would have more species because they were moving around less and being disturbed less. So when we actually look at data on species number, so the force class just refers to the size, it's how much force is required to move them. What we see with the X bar, which is the mean number of species on each of those census states, that in fact the medium-sized boulders have the most species. Okay, so first the scientists asked the question, why is there low species diversity on small boulders? And to do this, he devised an experiment. So he took the small rocks and he sterilized them using a blowtorch. So he started with no algal species. Then he immobilized half the rocks. So half were free to move, half weren't. And if it's the area hypothesis in play here, we might expect the species diversity among these two groups of rocks to be the same, right? Because area is the same. They're both small rocks. On the other hand, if the disturbance hypothesis, if the time hypothesis was playing the biggest role, then we might see a difference, right? Because half these rocks weren't able to move. So here's what was found. So month is on the x-axis, the percent cover on the y. And each species has its own line there, charting its area covered over time. And when you look, the stabilized small rocks on the top have more species than the unstable rocks on the bottom, suggesting that disturbance may have played at least some role in determining why the small rocks had fewer species. Okay, so that explains why the small rocks had fewer species than the medium-sized ones. But if it's just disturbance, if it's just time since disturbance, why didn't the largest boulders have even more species? Why do they support fewer algal species? And to get at that question, he looked at how much of the boulders were covered with algae and which species dominated. So again, we have the three different force classes there. And if we look, first of all, at the percent bare space in the largest boulders, we see that there's hardly any, right? As compared to the medium and small boulders. Okay. And then we look at dominating single species. And if we look particularly at GC to the right in that red rectangle, we see that on the largest boulders, sometimes it covered over 90%. So in these large boulders that weren't moving around, their algal community was dominated by a single species in many cases. So what was going on here? Well, in fact, it was competition. When those boulders were not moved around at all, there was nothing to keep the competitively dominant species from taking over. On the other hand, when the medium-sized boulders were rolling around, the competitively dominant species wasn't able to cover the whole rock because it would get rubbed off when these rocks were moving around, and it gave other species a chance to hang out. So it's interesting, the time hypothesis predicted that disturbance would decrease the number of species. But this example shows us that in some cases, a moderate level of disturbance might actually increase the number of species. So this is what's known as the intermediate disturbance hypothesis. And so on the x-axis to the left, we have habitats that are hardly ever disturbed. And they have low diversity because of a competitive dominant species that takes over. But on the opposite extreme, habitats that are disturbed quite a lot, they have low species diversity because there aren't many species that can live there. So that's why we get kind of this rainbow-looking plot of species diversity relative to disturbance frequency. Now, I think this is an important hypothesis to understand because a lot of our habitats are disturbed now to some degree or another. And so it's an important thing to think about as ecologists as to whether disturbance increases the number of species or decreases. Because that might determine the extent to which we try to stop disturbance in a habitat, for example. Okay. So we're just going to get a little bit into Chapter 3, and all of the material in today's lecture is fair game for the exam on Wednesday. So population ecology is where we're studying how populations grow and then what factors promote and limit population growth. And let's just step back for a moment and think about how it is that populations grow to begin with. So we want to get at something called the per capita growth rate. This is an important value for population ecologists to have. And so I'll walk you through how we'd calculate that value. So if we're looking at the change of numbers over change in time, right? In other words, how much does that population change over a time interval, which is most often a year, but not always. We could simply think of it as the number of births minus the number of deaths in that time. So yeah, if we're talking about like the population of squirrels at UNCA, over 1 year, how many births took place in that population, how many deaths took place. We subtract those and we'll get the change, assuming what we call a closed population. In other words, squirrels aren't coming and going. Well, then what we can do is divide the total number of births by capital N, which is the population size. And if we do that, we get lowercase b, which is the per capita birth, and I did not fix this, the per capita birth rate, not the per capita birth rate. So lowercase b is the per capita birth rate. It's the number of births per individual that took place in that time interval. We can do the same thing with deaths, divide the total number of deaths by the population size to get the per capita death rate. So that's like per individual, on average, how many deaths occurred in the population. Okay, then if we subtract our per capita death rate from our per capita birth rate, that gives us what's known as a per capita growth rate. And this is an important variable for population ecologists, and it's referred to as just a lowercase r. So one way to think about that is the change in population size. So delta n is population size. That delta is just a symbol that we use to denote change. So change in population size over a certain change in time is equal to our population size times little r. So if little r is 0, our population is not growing. We're not adding or subtracting individuals. If little r is positive, that means we have more births than deaths, and so our population is growing. If our population is, if little r is less than 0, then our population is shrinking. So if we think about how the population grows when r is positive, we need to keep in mind this fact that as our population grows, the number of individuals we add in each generation gets more and more. So for a per capita growth rate of 0.1, if our population is 10, we're only going to add 1 individual. But if our population is 100, we're going to add 10 individuals. So the interesting thing is that as long as r is positive, we will experience exponential growth. Now, the extent to which it accelerates and how fast it accelerates will depend on how high the value of r is, but we will have that exponential growth. So then I asked if exponential growth occurs very often in nature, and what we decided is that it can only occur if there are no limiting resources. So if we haven't hit Malthus's point of crisis. So for instance, this is an example of elk in Point Reyes National Seashore in California, where the population had been hunted basically to extinction during the California gold rush. They reintroduced these elk to Point Reyes. The population increased exponentially because there were no other species using the resources that the elk needed, and so the population just grew as if it was unlimited. It did not hit that point of crisis. At least it hadn't yet. So what about if resources are limiting? Well, if that's the case, then we see a curve that looks more like this. We call it a logistical growth curve, or an S growth curve. And so you can see it starts off as an exponential growth curve, but then it slows down, and around what we call the point of inflection, where the slope stops accelerating and begins to decelerate, that's where resources become limiting. And that limit is given by K, which is known as the carrying capacity. So this is what we call logistic population growth. So logistic, or an S curve, as opposed to an exponential, or what you might call a J curve. And you don't need to know those equations there.